Electromagnetic Induction. Introduction. Electricity and magnetism were considered separate and unrelated phenomena for a long time. In the early decades of the 19th century, experiments on electric current by Oersted, Ampere, and a few others established the fact that electricity and magnetism are interrelated. They found that moving electric charges produce magnetic fields. For example, an electric current deflects a magnetic compass needle placed in its vicinity. This naturally raises the questions like, is the converse effect possible? Can moving magnets produce electric currents? Does nature permit such a relation between electricity and magnetism? The answer is a resounding yes. The experiments of Michael Faraday in England and Joseph Henry in the USA, conducted around 1830, demonstrated conclusively that electric currents were induced in closed coils when subjected to changing magnetic fields. In this chapter, we will study the phenomena associated with changing magnetic fields and understand the underlying principles. The phenomenon in which electric current is generated by varying magnetic fields is appropriately called electromagnetic induction. When Faraday first made public his discovery that relative motion between a bar magnet and a wire loop produced a small current in the latter, he was asked, "What is the use of it?" His reply was, "What is the use of a newborn baby?" The phenomenon of electromagnetic induction is not merely of theoretical or academic interest but also of practical utility. Imagine a world where there is no electricity, no electric lights, no trains, no telephones, and no personal computers. The pioneering experiments of Faraday and Henry have led directly to the development of modern-day generators and transformers. Today's civilization owes its progress to a great extent to the discovery of electromagnetic induction. Experiments of Faraday and Henry. The discovery and understanding of electromagnetic induction are based on a long series of experiments carried out by Faraday and Henry. We shall now describe some of these experiments. Experiment 1. The figure shows coil C1 connected to a galvanometer G. When the north pole of a bar magnet is pushed towards the coil, the pointer in the galvanometer deflects, indicating the presence of electric current in the coil. The deflection lasts as long as the bar magnet is in motion. The galvanometer does not show any deflection when the magnet is held stationary. When the magnet is pulled away from the coil, the galvanometer shows deflection in the opposite direction, which indicates a reversal of the current's direction. Moreover, when the south pole of the bar magnet is moved towards or away from the coil, the deflections in the galvanometer are opposite to that observed with the north pole for similar movements. Further, the deflection and hence current is found to be larger when the magnet is pushed towards or pulled away from the coil faster. Instead, when the bar magnet is held fixed and coil C1 is moved towards or away from the magnet, the same effects are observed. It shows that it is the relative motion between the magnet and the coil that is responsible for the generation, that is, induction of electric current in the coil. Experiment 2. In figure, the bar magnet is replaced by a second coil C2 connected to a battery. The steady current in coil C2 produces a steady magnetic field. As coil C2 is moved towards coil C1, the galvanometer shows a deflection. This indicates that electric current is induced in coil C1. When C2 has moved away, the galvanometer shows a deflection again, but this time in the opposite direction. The deflection lasts as long as coil C2 is in motion. When coil C2 is held fixed and C1 is moved, the same effects are observed. Experiment 3. The above two experiments involved relative motion between a magnet and a coil and between two coils, respectively. Through another experiment, Faraday showed that this relative motion is not an absolute requirement. The figure shows two coils, C1 and C2 held stationary. Coil C1 is connected to galvanometer G, while the second coil C2 is connected to a battery through a tapping key K. It is observed that the galvanometer shows a momentary deflection when the tapping key K is pressed. The pointer in the galvanometer returns to 0 immediately. If the key is held pressed continuously, there is no deflection in the galvanometer. When the key is released, a momentary deflection is observed again, but in the opposite direction. It is also observed that the deflection increases dramatically when an iron rod is inserted into the coils along their axis. Magnetic flux. Faraday's great insight lay in discovering a simple mathematical relation to explaining the series of experiments he carried out on electromagnetic induction. However, before we state and appreciate his laws, we must get familiar with the notion of magnetic flux, phi b. Magnetic flux is defined in the same way as electric flux. Magnetic flux through a plane of area A placed in a uniform magnetic field B can be written as phi b is equal to B into A is equal to BA cos theta, equation 1, where theta is the angle between B and A. Equation 1 can be extended to curved surfaces and non-uniform fields. If the magnetic field has different magnitudes and directions at various parts of a surface as shown in figure, then the magnetic flux through the surface is given by phi b is equal to B1 into dA1 plus B2 into dA2 plus up to so on is equal to summation all Bi into dAi, equation 2, where all stands for summation over all the area elements dAi, comprising the surface, and Bi is the magnetic field at the area element dAi. The SI unit of magnetic flux is Weber or Tesla meter squared. Magnetic flux is a scalar quantity. Faraday's law of induction. From the experimental observations, Faraday arrived at a conclusion that an electromotive force is induced in a coil when magnetic flux through the coil changes with time. Experimental observations discussed in previous section can be explained using this concept. The motion of a magnet towards or away from coil C1 in experiment 1 and moving a current carrying coil C2 towards or away from coil C1 in experiment 2 change the magnetic flux associated with coil C1. The change in magnetic flux induces electromotive force in coil C1. It was this induced electromotive force that caused an electric current to flow in coil C1 and through the galvanometer. A plausible explanation for the observations of experiment 3 is as follows. When the tapping key K is pressed, the current in coil C2 and the resulting magnetic field rises from 0 to a maximum value in a short time. Consequently, the magnetic flux through the neighboring coil C1 also increases. It is the change in magnetic flux through coil C1 that produces an induced electromotive force in coil C1. When the key is held pressed, the current in coil C2 is constant. Therefore, there is no charge in the magnetic flux through coil C1 and the current in coil C1 drops to 0. When the key is released, the current in C2 and the resulting magnetic field decrease from the maximum value to 0 in a short time. This results in a decrease in magnetic flux through coil C1 and hence again induces an electric current in coil C1. The common point in all these observations is that the time rate of change of magnetic flux through a circuit induces electromotive force in it. Faraday stated experimental observations in the form of a law called Faraday's law of electromagnetic induction. The law is stated below. The magnitude of the induced electromotive force in a circuit is equal to the time rate of change of magnetic flux through the circuit. Mathematically, the induced electromotive force is given by epsilon is equal to minus d phi b upon dt. Equation 3. The negative sign indicates the direction of epsilon and hence the direction of current in a closed loop. In the case of closely wound coil of n turns, the change of flux associated with each turn is the same. Therefore, the expression for the total induced electromotive force is given by epsilon is equal to minus n into d phi b upon dt. Equation 4. The induced electromotive force can be increased by increasing the number of turns n of a closed coil. From equations 1 and 2, we see that the flux can be varied by changing any one or more of the terms B, A and theta in experiments 1 and 2. The flux is changed by varying B. The flux can also be altered by changing the shape of a coil, that is, by shrinking it or stretching it in a magnetic field or rotating a coil in a magnetic field such that the angle theta between B and A changes. In these cases too, an electromotive force is induced in the respective coils. Example 1. Consider experiment 2. A. What would you do to obtain a large deflection of the galvanometer? B. How would you demonstrate the presence of an induced current in the absence of a galvanometer? Solution. A. To obtain a large deflection, one or more of the following steps can be taken. Number 1. Use a rod made of soft iron inside the coil C2. Number 2. Connect the coil to a powerful battery. And number 3. Move the arrangement rapidly towards the test coil C1. B. Replace the galvanometer with a small bulb, the kind one finds in the small torchlight. The relative motion between the two coils will cause the bulb to glow and thus demonstrate the presence of an induced current. Example 2. A square loop of side 10 cm and resistance 0.5 ohm is placed vertically in the east-west plane. A uniform magnetic field of 0.10 Tesla is set up across the plane in the northeast direction. The magnetic field is decreased to 0 in 0.70 second at a steady rate. Determine the magnitudes of induced electromotive force and current during this time interval. Solution. The angle theta made by the area vector of the coil with the magnetic field is 45 degree. The initial magnetic flux is phi is equal to BA cos theta is equal to 0.1 into 10 raised to minus 2 upon root 2 Weber. Final flux phi minimum is equal to 0. The change in flux is brought about in 0.70 second. The magnitude of the induced electromotive force is given by epsilon is equal to modulus of delta phi b upon delta t is equal to modulus of phi minus 0 upon delta t is equal to 10 raised to minus 3 upon root 2 into 0.7 is equal to 1.0 millivolt. And the magnitude of the current is I is equal to epsilon upon R is equal to 10 raised to minus 3 volt upon 0.5 ohm is equal to 2 milliampere. Example 3. A circular coil of radius 10 cm, 500 turns and resistance 2 ohm is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. It is rotated about its vertical diameter through 180 degree in 0.25 second. Estimate the magnitudes of the electromotive force and current induced in the coil. The horizontal component of the Earth's magnetic field at the place is 3.0 into 10 raised to minus 5 Tesla. Solution. Initial flux through the coil phi b initial is equal to BA cos theta is equal to 3.0 into 10 raised to minus 5 into pi into 10 raised to minus 2 into cos 0 degree is equal to 3 pi into 10 raised to minus 7 Weber. Final flux after the rotation phi b final is equal to 3.0 into 10 raised to minus 5 into pi into 10 raised to minus 2 into cos 180 degree is equal to minus 3 pi into 10 raised to minus 7 Weber. Therefore, estimated value of the induced electromotive force is epsilon is equal to n into delta phi b upon delta t is equal to 500 into 6 pi into 10 raised to minus 7 upon 0.25 is equal to 3.8 into 10 raised to minus 3 volt. I is equal to epsilon upon R is equal to 1.9 into 10 raised to minus 3 ampere. Lenz law and conservation of energy. In 1834, German physicist Heinrich Friedrich Lenz 1804 to 1865 deduced a rule known as Lenz's law, which gives the polarity of the induced electromotive force in a clear and concise fashion. The polarity of induced electromotive force is such that it tends to produce a current which opposes the change in magnetic flux that produced it. The negative sign shown in equation 3 represents this effect. In figure, we see that the north pole of a bar magnet is being pushed towards the closed coil. As the north pole of the bar magnet moves towards the coil, the magnetic flux through the coil increases. Hence, current is induced in the coil in such a direction that it opposes the increase in flux. This is possible only if the current in the coil is in a counterclockwise direction with respect to an observer situated on the side of the magnet. The magnetic moment associated with this current has north polarity towards the north pole of the approaching magnet. Similarly, if the north pole of the magnet is being withdrawn from the coil, the magnetic flux through the coil will decrease. To counter this decrease in magnetic flux, the induced current in the coil flows in a clockwise direction and its south pole faces the receding north pole of the bar magnet. This would result in an attractive force that opposes the motion of the magnet and the corresponding decrease in flux. What will happen if an open circuit is used in place of the closed loop in the above example? In this case too, an electromotive force is induced across the open ends of the circuit. The direction of the induced electromotive force can be found using Lenz's law. Consider figures. They provide an easier way to understand the direction of induced currents. A little reflection on this matter should convince us of the correctness of Lenz's law. Suppose that the induced current was in the direction opposite to the one depicted in figure. In that case, the south pole due to the induced current will face the approaching north pole of the magnet. The bar magnet will then be attracted towards the coil at an ever increasing acceleration. A gentle push on the magnet will initiate the process, and its velocity and kinetic energy will continuously increase without expending any energy. If this can happen, one could construct a perpetual motion machine by a suitable arrangement. This violates the law of conservation of energy and hence cannot happen. Now consider the correct case shown in figure. In this situation, the bar magnet experiences a repulsive force due to the induced current. Therefore, a person has to do work in moving the magnet. Where does the energy spent by the person go? This energy is dissipated by joule heating produced by the induced current. Example 4. The figure shows planar loops of different shapes moving out of or into a region of a magnetic field which is directed normally to the plane of the loop away from the reader. Determine the direction of induced current in each loop using Lenz's law. Solution. Number 1. The magnetic flux through the rectangular loop ABCD increases. Due to the motion of the loop into the region of the magnetic field, the induced current must flow along the path BCDAB so that it opposes the increasing flux. Number 2. Due to the outward motion, the magnetic flux through the triangular loop ABC decreases, due to which the induced current flows along BACB so as to oppose the change in flux. Number 3. As the magnetic flux decreases due to the motion of the irregularly shaped loop ABCD out of the region of the magnetic field, the induced current flows along CDABC so as to oppose change in flux. Example 5. A. A closed loop is held stationary in the magnetic field between the north and south poles of two permanent magnets held fixed. Can we hope to generate current in the loop by using very strong magnets? B. A closed loop moves normally to the constant electric field between the plates of a large capacitor. Is a current induced in the loop 1. When it is wholly inside the region between the capacitor plates, and 2. When it is partially outside the plates of the capacitor? The electric field is normal to the plane of the loop. C. A rectangular loop and a circular loop are moving out of a uniform magnetic field region to a field-free region with a constant velocity v. In which loop do you expect the induced electromotive force to be constant during the passage out of the field region? The field is normal to the loops. D. Predict the polarity of the capacitor in the situation described in figure. Solution. A. However strong the magnet may be, current can be induced only by changing the magnetic flux through the loop. B. No current is induced in either case. Current cannot be induced by changing the electric flux. C. The induced electromotive force is expected to be constant only in the case of the rectangular loop. In the case of a circular loop, the rate of change of the area of the loop during its passage out of the field region is not constant. Hence, induced electromotive force will vary accordingly. D. The polarity of plate A will be positive with respect to plate B in the capacitor. Motional electromotive force. Let us consider a straight conductor moving in a uniform and time-independent magnetic field. The figure shows a rectangular conductor PQRS in which the conductor PQ is free to move. The rod PQ is moved towards the left with a constant velocity of v as shown in the figure. Assume that there is no loss of energy due to friction. PQRS forms a closed circuit enclosing an area that changes as PQ moves. It is placed in a uniform magnetic field which is perpendicular to the plane of this system. If the length RQ is equal to x and Rs is equal to L, the magnetic flux phi b enclosed by the loop PQRS will be phi b is equal to BLX. Since x is changing with time, the rate of change of flux phi b will induce an electromotive force given by epsilon is equal to minus d phi b upon dt is equal to minus d upon dt BLX is equal to minus BL dx by dt is equal to BLV, equation 5, where we have used dx upon dt is equal to minus v, which is the speed of the conductor PQ. The induced electromotive force BLV is called Motional electromotive force. Thus, we are able to produce induced electromotive force by moving a conductor instead of varying the magnetic field, that is, by changing the magnetic flux enclosed by the circuit. It is also possible to explain the motional electromotive force expression in equation 5 by invoking the Lorentz force acting on the free charge carriers of conductor PQ. Consider any arbitrary charge Q in the conductor PQ. When the rod moves with speed v, the charge will also be moving with speed v in the magnetic field B. The Lorentz force on this charge is QVB in magnitude and its direction is towards Q. All charges experience the same force in magnitude and direction irrespective of their position in the rod PQ. The work done in moving the charge from P to Q is W is equal to QVPL. Since electromotive force is the work done per unit charge, epsilon is equal to W upon Q is equal to BLV. This equation gives electromotive force induced across the rod PQ and is identical to equation 5. We stress that our presentation is not wholly rigorous, but it does help us to understand the basis of Faraday's law when the conductor is moving in a uniform and time-independent magnetic field. On the other hand, it is not obvious how an electromotive force is induced when a conductor is stationary and the magnetic field is changing, a fact that Faraday verified by numerous experiments. In the case of a stationary conductor, the force on its charges is given by F is equal to Q into E plus V into B is equal to QE. Equation 6. Since V is equal to 0, thus any force on the charge must arise from the electric field term E alone. Therefore, to explain the existence of induced electromotive force or induced current, we must assume that a time-varying magnetic field generates an electric field. However, we hasten to add that electric fields produced by static electric charges have properties different from those produced by time-varying magnetic fields. We learned that charges in motion, that is current, can exert force or torque on a stationary magnet. Conversely, a bar magnet in motion, or more generally a changing magnetic field, can exert a force on the stationary charge. This is the fundamental significance of Faraday's discovery. Electricity and magnetism are related. Example 6. A metallic rod of 1 meter length is rotated with a frequency of 50 revolutions per second, with one end hinged at the center and the other end at the circumference of a circular metallic ring of radius 1 meter about an axis passing through the center and perpendicular to the plane of the ring. A constant and uniform magnetic field of 1 Tesla parallel to the axis is present everywhere. What is the electromotive force between the center and the metallic ring? Solution. Method 1. As the rod is rotated, free electrons in the rod move towards the outer end due to Lorentz force and get distributed over the ring. Thus, the resulting separation of charges produces an electromotive force across the ends of the rod. At a certain value of electromotive force, there is no more flow of electrons and a steady state is reached. Using equation 5, the magnitude of the electromotive force generated across a length dr of the rod as it moves at right angles to the magnetic field is given by d epsilon is equal to bv dr. Hence, epsilon is equal to integration d epsilon is equal to integration 0 to r bv dr is equal to integration 0 to r b omega r dr is equal to b omega r square upon 2. Note that we have used v is equal to omega r. This gives epsilon is equal to 1 upon 2 into 1.0 into 2 pi into 50 into 1 square is equal to 157 volt. Method 2. To calculate the electromotive force, we can imagine a closed loop OPQ in which points O and P are connected with a resistor R and OQ is the rotating rod. The potential difference across the resistor is then equal to the induced electromotive force and equals B into rate of change of the area of the loop. If theta is the angle between the rod and the radius of the circle at P at time t, the area of the sector OPQ is given by pi r square into theta upon 2 pi is equal to 1 upon 2 r square theta, where r is the radius of the circle. Hence, the induced electromotive force is epsilon is equal to b into d upon dt into 1 upon 2 r square theta is equal to 1 upon 2 b r square d theta upon dt is equal to b omega r square upon 2. Note, d theta upon dt is equal to omega is equal to 2 pi v. This expression is identical to the expression obtained by method 1 and we get the same value of epsilon. Example 7. A wheel with 10 metallic spokes, each 0.5 meter long, is rotated with a speed of 120 revolution per minute in a plane normal to the horizontal component of Earth's magnetic field HE at a place. If HE is equal to 0.4 Gauss at the place, what is the induced electromotive force between the axle and the rim of the wheel? Note that 1 Gauss is equal to 10 raised to minus 4 Tesla. Solution. Induced electromotive force is equal to 1 upon 2 omega b r square is equal to 1 upon 2 into 4 pi into 0.4 into 10 raised to minus 4 into 0.5 whole square is equal to 6.28 into 10 raised to minus 5 volt. The number of spokes is immaterial because the electromotive forces across the spokes are in parallel. Energy consideration, a quantitative study. In previous section, we discussed qualitatively that Lenz's law is consistent with the law of conservation of energy. Now we shall explore this aspect further with a concrete example. Let R be the resistance of movable arm PQ of the rectangular conductor shown in figure. We assume that the remaining arms QR, RS and SP have negligible resistances compared to R. Thus, The overall resistance of the rectangular loop is R, and this does not change as PQ is moved. The current I in the loop is I is equal to epsilon upon R is equal to BLV upon R. Equation 7. On account of the presence of the magnetic field, there will be a force on the arm PQ. This force I into L into B is directed outwards in the direction opposite to the velocity of the rod. The magnitude of this force is F is equal to ILB is equal to B square L square V upon R, where we have used equation 7. Note that this force arises due to drift velocity of charges responsible for current along the rod and the consequent Lorentz force acting on them. Alternatively, the arm PQ is being pushed with a constant speed V. The power required to do this is P is equal to FV is equal to B square L square V square upon R. Equation 8. The agent that does this work is mechanical. Where does this mechanical energy go? The answer is it is dissipated as joule heat and is given by Pj is equal to I square R is equal to BLV upon R whole square into R is equal to B square L square V square upon R, which is identical to equation 8. Thus, mechanical energy which was needed to move the arm PQ is converted into electrical energy, that is, the induced electromotive force, and then to thermal energy. There is an interesting relationship between the charge flow through the circuit and the change in the magnetic flux. From Faraday's law, we have learnt that the magnitude of the induced electromotive force is modulus of epsilon is equal to delta phi b upon delta t. However, modulus of epsilon is equal to IR is equal to delta Q upon delta T into R. Thus, delta Q is equal to delta phi b upon R. Example 8. Refer to figure. The arm PQ of the rectangular conductor is moved from x is equal to 0 outwards. The uniform magnetic field is perpendicular to the plane and extends from x is equal to 0 to x is equal to b and is 0 for x is greater than b. Only the arm PQ possesses substantial resistance R. Consider the situation when the arm PQ is pulled outwards from x is equal to 0 to x is equal to 2b and is then moved back to x is equal to 0 with constant speed v. Obtain expressions for the flux, the induced electromotive force, the force necessary to pull the arm, and the power dissipated as joule heat. Sketch the variation of these quantities with distance. Solution. Let us first consider the forward motion from x is equal to 0 to x is equal to 2b. The flux phi b linked with the circuit SPQR is phi b is equal to BLX, where 0 is less than or equal to x is less than b is equal to BLB, where b is less than or equal to x is less than 2b. The induced electromotive force is epsilon is equal to minus d phi b upon dt is equal to minus BLV, where 0 is less than or equal to x less than b is equal to 0, where b is less than or equal to x is less than 2b. When the induced electromotive force is non-zero, the current I is in magnitude. I is equal to BLV upon R. The force required to keep the arm PQ in constant motion is ILB. Its direction is to the left. In magnitude, F is equal to B square L square V upon R, where 0 is less than or equal to x is less than b is equal to 0, where b is less than or equal to x is less than 2b. The joule heating loss is Pj is equal to I square R. is equal to b square L square V square upon R, where 0 is less than or equal to x is less than b is equal to 0, where b is less than or equal to x is less than 2b. One obtains similar expressions for the inward motion from x is equal to 2b to x is equal to 0. One can appreciate the whole process by examining the sketch of various quantities displayed in figure. Eddy currents. So far we have studied the electric currents induced in well-defined paths in conductors like circular loops. Even when bulk pieces of conductors are subjected to changing magnetic flux, induced currents are produced in them. However, their flow patterns resemble swirling eddies in the water. This effect was discovered by physicist Foucault in 1819 to 1868, and these currents are called eddy currents. Consider the apparatus shown in figure. A copper plate is allowed to swing like a simple pendulum between the pole pieces of a strong magnet. It is found that the motion is damped and in a little while the plate comes to a halt in the magnetic field. We can explain this phenomenon on the basis of electromagnetic induction. Magnetic flux associated with the plate keeps on changing as the plate moves in and out of the region between magnetic poles. The flux change induces eddy currents in the plate. Directions of eddy currents are opposite when the plate swings into the region between the poles and when it swings out of the region. If rectangular slots are made in the copper plate as shown in figure, the area available for the flow of eddy currents is less. Thus, the pendulum plate with holes or slots reduces electromagnetic damping and the plate swings more freely. Note that magnetic moments of the induced currents which oppose the motion depend upon the area enclosed by the currents. This fact is helpful in reducing eddy currents in the metallic cores of transformers, electric motors, and other such devices in which a coil is to be wound over a metallic core. Eddy currents are undesirable since they heat up the core and dissipate electrical energy in the form of heat. Eddy currents are minimized by using laminations of metal to make a metal core. The laminations are separated by an insulating material like lacquer. The plane of the laminations must be arranged parallel to the magnetic field so that they cut across the eddy current paths. This arrangement reduces the strength of the eddy currents, since the dissipation of electrical energy into heat depends on the square of the strength of the electric current. Heat loss is substantially reduced. Eddy currents are used to advantage in certain applications like number 1. Magnetic braking in trains. Strong electromagnets are situated above the rails in some electrically powered trains. When the electromagnets are activated, the eddy currents induced in the rails oppose the motion of the train. As there are no mechanical linkages, the braking effect is smooth. Number 2. Electromagnetic damping. Certain galvanometers have a fixed core made of non-magnetic metallic material. When the coil oscillates, the eddy currents generated in the core oppose the motion and bring the coil to rest quickly. Number 3. Induction furnace. Induction furnace can be used to produce high temperatures and can be utilized to prepare alloys by melting the constituent metals. A high-frequency alternating current is passed through a coil that surrounds the metals to be melted. The eddy currents generated in the metals produce high temperatures sufficient to melt them. Number 4. Electric power meters. The shiny metal disc in the electric power meter, that is analog type, rotates due to the eddy currents. Electric currents are induced in the disc by magnetic fields produced by sinusoidally varying currents in a coil. You can observe the rotating shiny disc in the power meter of your house. Electromagnetic damping. Take two hollow thin cylindrical pipes of equal internal diameters made of aluminium and PVC respectively. Fix them vertically with clamps on retort stands. Take a small cylindrical magnet having a diameter slightly smaller than the inner diameter of the pipes and drop it through each pipe in such a way that the magnet does not touch the sides of the pipes during its fall. You will observe that the magnet dropped through the PVC pipe takes the same time to come out of the pipe as it would take when dropped through the same height without the pipe. Note the time it takes to come out of the pipe in each case. You will see that the magnet takes a much longer time in the case of aluminium pipe. Why is it so? It is due to the eddy currents that are generated in the aluminium pipe which oppose the change in magnetic flux, that is, the motion of the magnet. The retarding force due to the eddy currents inhibits the motion of the magnet. Such phenomena are referred to as electromagnetic damping. Note that eddy currents are not generated in PVC pipe as its material is an insulator, whereas aluminum is a conductor. Inductance. An electric current can be induced in a coil by flux change produced by another coil in its vicinity or flux change produced by the same coil. However, in both the cases, the flux through a coil is proportional to the current, that is, phi b is proportional to I. Further, if the geometry of the coil does not vary with time, then d phi b upon dt is proportional to di upon dt. For a closely wound coil of n turns, the same magnetic flux is linked with all the turns. When the flux phi b through the coil changes, each turn contributes to the induced electromotive force. Therefore, a term called flux linkage is used, which is equal to n phi b for a closely wound coil, and in such a case n phi b is proportional to I. The constant of proportionality in this relation is called inductance. We shall see that inductance depends only on the geometry of the coil and intrinsic material properties. This aspect is akin to capacitance, which for a parallel plate capacitor depends on the plate area and plate separation, that is geometry, and the dielectric constant K of the intervening medium, that is intrinsic material property. Inductance is a scalar quantity. It has the dimensions of ml square t raised to minus 2 a raised to minus 2, given by the dimensions of flux divided by the dimensions of current. The SI unit of inductance is Henry and is denoted by H. It is named in honor of Joseph Henry, who discovered electromagnetic induction in USA, independently of Faraday in England. Mutual inductance, which shows two long coaxial solenoids each of length L. We denote the radius of the inner solenoid S1 by R1 and the number of turns per unit length by N1. The corresponding quantities for the outer solenoid S2 are R2 and N2 respectively. Let N1 and N2 be the total number of turns of coils S1 and S2 respectively. When a current I2 is set up through S2, it in turn sets up a magnetic flux through S1. Let us denote it by phi1. The corresponding flux linkage with solenoid S1 is N1 is equal to M12I2. Equation 9. M12 is called the mutual inductance of solenoid S1 with respect to solenoid S2. It is also referred to as the coefficient of mutual induction. For these simple coaxial solenoids, it is possible to calculate M12. The magnetic field due to the current I2 in S2 is mu0 N2 I2. The resulting flux linkage with coil S1 is N1 is equal to N1L into pi R1 square into mu0 N2 I2 is equal to mu0 N1 N2 pi R1 square L I2. Equation 10, where N1L is the total number of turns in solenoid S1. Thus, from equation 9 and equation 10, M12 is equal to mu0 N1 N2 pi R1 square L. Equation 11. Note that we neglected the edge effects and considered the magnetic field mu0 N2 I2 to be uniform throughout the length and width of the solenoid S2. This is a good approximation, keeping in mind that the solenoid is long, implying L is very much greater than R2. We now consider the reverse case. A current I1 is passed through the solenoid S1 and the flux linkage with coil S2 is N2 is equal to M21 I1. Equation 12. M21 is called the mutual inductance of solenoid S2 with respect to solenoid S1. The flux due to the current I1 in S1 can be assumed to be confined solely inside S1 since the solenoids are very long. Thus, flux linkage with solenoid S2 is N2 is equal to N2L into pi R1 square into mu0 N1 I1, where N2L is the total number of turns of S2. From equation 12, M21 is equal to mu0 N1 N2 pi R1 square L. Equation 13. Using equation 11 and equation 30, we get M12 is equal to M21 is equal to M. Say equation 14. We have demonstrated this equality for long coaxial solenoids. Note that if the inner solenoid was much shorter than and placed well inside the outer solenoid, then we could still have calculated the flux linkage N1 because the inner solenoid is effectively immersed in a uniform magnetic field due to the outer solenoid. In this case, the calculation of M12 would be easy. However, it would be extremely difficult to calculate the flux linkage with the outer solenoid as the magnetic field due to the inner solenoid would vary across the length as well as cross section of the outer solenoid. Therefore, the calculation of M21 would also be extremely difficult in this case. The equality M12 is equal to M21 is very useful in such situations. We explained the above example with air as the medium within the solenoids. Instead, if a medium of relative permeability μr had been present, the mutual inductance would be M is equal to μr mu0 N1 N2 pi R1 square L. It is also important to know that the mutual inductance of a pair of coils, solenoids, etc. depends on their separation as well as their relative orientation. Example 9. Two concentric circular coils, one of small radius R1 and the other of large radius R2, such that R1 is very much less than R2, are placed coaxially with centers coinciding. Obtain the mutual inductance of the arrangement. Solution. Let a current I2 flow through the outer circular coil. The field at the center of the coil is B2 is equal to mu0 I2 upon 2 R2. Since the outer coaxially placed coil has a very small radius, B2 may be considered constant over its cross-sectional area. Hence, phi 1 is equal to pi R1 square B2 is equal to mu0 pi R1 square upon 2 R2 into I2 is equal to M12 I2. Thus, M12 is equal to mu0 pi R1 square upon 2 R2. From equation 14, M12 is equal to M21 is equal to mu0 pi R1 square upon 2 R2. Now, let us recollect experiment 3 in previous section. In that experiment, electromotive force is induced in coil C1 wherever there was any change in current through coil C2. Let phi 1 be the flux through coil C1, say of N1 turns when current in coil C2 is I2. Then, from equation 9, we have N1 phi 1 is equal to Mi2. For currents varying with time, d N1 phi 1 upon dt is equal to d Mi2 upon dt. Since induced electromotive force in coil C1 is given by epsilon 1 is equal to minus d N1 phi 1 upon dt, we get epsilon 1 is equal to minus m di2 upon dt. It shows that varying current in a coil can induce electromotive force in a neighboring coil. The magnitude of the induced electromotive force depends upon the rate of change of current and mutual inductance of the two coils. Self-inductance. In the previous subsection, we considered the flux in one solenoid due to the current in the other. It is also possible that electromotive force is induced in a single isolated coil due to a change of flux through the coil by means of varying the current through the same coil. This phenomenon is called self-induction. In this case, flux linkage through a coil of N turns is proportional to the current through the coil and is expressed as N phi B is proportional to I. N phi B is equal to Li, equation 15, where the constant of proportionality L is called the self-inductance of the coil. It is also called the coefficient of self-induction of the coil. When the current is varied, the flux linked with the coil also changes, and an electromotive force is induced in the coil. Using equation 15, the induced electromotive force is given by epsilon is equal to minus d N phi B upon dt. Epsilon is equal to minus L di upon dt. Equation 16. Thus, the self-induced electromotive force always opposes any change, that is, increase or decrease of current in the coil. It is possible to calculate the self-inductance for circuits with simple geometries. Let us calculate the self-inductance of a long solenoid of cross-sectional area A and length L, having N turns per unit length. The magnetic field due to a current I flowing in the solenoid is B is equal to mu0 Ni. Neglecting age effects as before, the total flux linked with the solenoid is N phi B is equal to NL into mu0 Ni into A is equal to mu0 N square ALI, where NL is the total number of turns. Thus, self-inductance is L is equal to N phi B upon I is equal to mu0 N square AL, equation 17. If we fill the inside of the solenoid with a material of relative permeability mu r, for example, soft iron which has a high value of relative permeability, then L is equal to mu r mu0 N square AL, equation 18. The self-inductance of the coil depends on its geometry and on the permeability of the medium. The self-induced electromotive force is also called the back electromotive force as it opposes any change in the current in a circuit. Physically, self-inductance plays the role of inertia. It is the electromagnetic analog of mass in mechanics. So, work needs to be done against the back electromotive force, that is epsilon, in establishing the current. This work is stored as magnetic potential energy. For the current I at an instant in a circuit, the rate of work done is dW upon dt is equal to modulus of epsilon into I. If we ignore the resistive losses and consider only the inductive effect, then using equation 16, dW upon dt is equal to Li di upon dt. The total amount of work done in establishing the current I is W is equal to integration dW is equal to integration 0 to I Li di. Thus, the energy required to build up the current I is W is equal to 1 upon 2 Li square. Equation 19. This expression reminds us of mv square upon 2 for the mechanical kinetic energy of a particle of mass m and shows that L is analogous to m. L is electrical inertia and opposes growth and decay of current in the circuit. Consider the general case of currents flowing simultaneously in two nearby coils. The flux linked with one coil will be the sum of two fluxes that exist independently. Equation 9 would be modified into N1 is equal to M11 I1 plus M12 I2, where M11 represents inductance due to the same coil. Therefore, using Faraday's law, epsilon 1 is equal to minus M11 di1 upon dt minus M12 di2 upon dt. M11 is the self-inductance and is written as L1. Therefore, epsilon 1 is equal to minus L1 di1 upon dt minus M12 di2 upon dt. Topic 610E. Example 10. A. Obtain the expression for the magnetic energy stored in a solenoid in terms of magnetic field B, area A and length L of the solenoid. B. How does this magnetic energy compare with the electrostatic energy stored in a capacitor? Solution A. From equation 19, the magnetic energy is UB is equal to 1 upon 2 Li square is equal to 1 upon 2 L into B upon mu 0 N whole square, since B is equal to mu 0 N I for a solenoid is equal to 1 upon 2 L into mu 0 N square AL into B upon mu 0 N whole square from equation 17 is equal to 1 upon 2 mu 0 B square AL. B. The magnetic energy per unit volume is small ub is equal to capital UB upon V, where V is volume that contains flux, is equal to UB upon AL is equal to B square upon 2 mu 0. Equation 20. We have already obtained the relation for the electrostatic energy stored per unit volume in a parallel plate capacitor. Refer to equation 77. UE is equal to 1 upon 2 epsilon 0 E square. Equation 77. In both the cases, energy is proportional to the square of the field strength. Equations 20 and 77 have been derived for special cases, a solenoid and a parallel plate capacitor respectively, but they are general and valid for any region of space in which a magnetic field and an electric field exist. AC generator. The phenomenon of electromagnetic induction has been technologically exploited in many ways. An exceptionally important application is the generation of alternating currents, that is AC. The modern AC generator with a typical output capacity of 100 megawatt is a highly evolved machine. In this section, we shall describe the basic principles behind this machine. The Yugoslav inventor Nikola Tesla is credited with the development of the machine. As was pointed out in section, one method to induce an electromotive force or current in a loop is through a change in the loop's orientation or a change in its effective area. As the coil rotates in a magnetic field B, the effective area of the loop, that is, the phase perpendicular to the field, is A cos theta, where theta is the angle between A and B. This method of producing a flux change is the principle of operation of a simple AC generator. An AC generator converts mechanical energy into electrical energy. The basic elements of an AC generator are shown in figure. It consists of a coil mounted on a rotor shaft. The axis of rotation of the coil is perpendicular to the direction of the magnetic field. The coil, called armature, is mechanically rotated in the uniform magnetic field by some external means. The rotation of the coil causes the magnetic flux through it to change. So an electromotive force is induced in the coil. The ends of the coil are connected to an external circuit by means of slip rings and brushes. When the coil is rotated with a constant angular speed omega, the angle theta between the magnetic field vector B and the area vector A of the coil at any instant t is theta is equal to omega t, assuming theta is equal to 0 degree at t is equal to 0. As a result, the effective area of the coil exposed to the magnetic field lines changes with time, and from equation 1, the flux at any time t is phi b is equal to Ba cos theta is equal to Ba cos omega t. From Faraday's law, the induced electromotive force for the rotating coil of n turns is then epsilon is equal to minus n d phi b upon dt is equal to minus nba d upon dt cos omega t. Thus, the instantaneous value of the electromotive force is epsilon is equal to nba omega sin omega t. Equation 21, where nba omega is the maximum value of the electromotive force, which occurs when sin omega t is equal to plus or minus 1. If we denote nba omega as epsilon 0, then epsilon is equal to epsilon 0 sin omega t. Equation 22. Since the value of the sine function varies between plus 1 and minus 1, the sign or polarity of the electromotive force changes with time. Note from figure that the electromotive force has its extremum value when theta is equal to 90 degree or theta is equal to 270 degree, as the change of flux is greatest at these points. The direction of the current changes periodically and therefore the current is called alternating current, that is AC. Since omega is equal to 2 pi v, equation 22 can be written as epsilon is equal to epsilon 0 sin 2 pi nu into t. Equation 23, where nu is the frequency of revolution of the generator's coil. Note that equation 22 and 23 give the instantaneous value of the electromotive force, and epsilon varies between plus epsilon 0 and minus epsilon 0 periodically. We shall learn how to determine the time averaged value for the alternating voltage and current in the next chapter. In commercial generators, the mechanical energy required for rotation of the armature is provided by water falling from a height, for example, from dams. These are called hydroelectric generators. Alternatively, water is heated to produce steam using coal or other sources. The steam at high pressure produces the rotation of the armature. These are called thermal generators instead of coal. If a nuclear fuel is used, we get nuclear power generators. Modern day generators produce electric power as high as 500 megawatt. That is, one can light up 5 million 100-volt bulbs. In most generators, the coils are held stationary and it is the electromagnets which are rotated. The frequency of rotation is 50 Hz in India. In certain countries such as USA, it is 60 Hz. Example 11. Kamla pedals a stationary bicycle. The pedals of the bicycle are attached to a 100-ton coil of area 0.10 meter square. The coil rotates at half a revolution per second and it is placed in a uniform magnetic field of 0.01 Tesla perpendicular to the axis of rotation of the coil. What is the maximum voltage generated in the coil? Solution. Here, nu is equal to 0.5 Hz, n is equal to 100, a is equal to 0.1 meter square and b is equal to 0.01 Tesla. Employing equation 21. Epsilon 0 is equal to NBA into 2 pi nu is equal to 100 into 0.01 into 0.1 into 2 into 3.14 into 0.5 is equal to 0.314 volt. The maximum voltage is 0.314 volt. We urge you to explore such alternative possibilities for power generation.